Now, you also studied psychology, the human brain in your undergrad. How does that compare to what we have in our brains?
So we have about 100 million synapses. And even though many of them are used for other things like breathing, the cortex, the neocortex, has most of those. So we've got many more adaptable parameters than these big language models, which makes it very strange that GPT-4 knows thousands of times more than we do.
And you said 100 million. I think you meant 100 trillion.
Did I say 100 million?
I think you said 100 million.
I could be a politician. I can't tell the difference between millions and trillions. They are not very good expert at everything. So they know thousands of times more than any one person. And one of the reasons it can do that is you can have many different copies of exactly the same neural net running on different hardware. So you can get one copy to look at this bit of the internet, another copy to look at that bit of the internet. They can both figure out how they'd like to change their own weights. And if you just average those changes, then both copies have learned from the experience that each of them had. So now take 1,000 of those. Imagine if we could take 1,000 people, they could all go off and do a different course, and at the end, everyone knew what everyone had experienced.
We've talked a little bit about memory and how memory is stored in the human brain. We've talked about sort of fast weights and how those can adjust. Is there anything missing in an LLM architecture that humans still do exceptionally better, the human brain does better?
I think we still learn better from limited data, and we don't quite know how we do that. We know the human brain has changes in connection strengths at many different timescales. So the first time I met Terry Sinofsky in 1979, that was basically the first thing we talked about, how these neural net models have just two timescales. They have the timescale of the activities of the neurons changing, and so each time you put in a different sentence, the neural activities will change. And then they have the activities of the values of the weights, the connection strengths, and they change very slowly. That's where all the knowledge is. And they just have those two timescales. Now you could have many more timescales. Let's just suppose you have one more timescale where you have weights. You have the weights that change slowly, but you have an overlay of weights that change much faster but decay quickly. That gives you all sorts of extra nice properties. So, for example, if I say an unexpected word to you like cucumber, and a couple of minutes later, I put headphones on you, and I put lots of noise in the headphones, and I play words so you can only just hear them. Most of them you can't quite make out what they are. You'll be considerably better at making out the word cucumber, because you heard it 2 minutes ago. So the question is, where is that stored? And it's not stored in neural activities. You can't afford to do that. You use up too many neurons. And it's not stored in the long-term weights, because in a few days' time it'll be gone. It's stored in short-term changes to the synapse strengths. And we don't have that in the models at present.
Can you share some examples of how introducing new information to an LLM that it might not have had in its training data, how it can reason over that and come up with an answer that's similar to how a human might reason by analogy?
Well, I can give a nice example of it doing analogies that most people can't do.
I would love to hear that.
So I asked GPT-4 some time ago when it wasn't hooked up to the web, why is a compost heap like an atom bomb?
And I would not be able to answer that question.
Excellent. So it said the time scales are very different and the energy scales are very different. And then it went on about chain reactions. It went on about how in a compost heap, the hotter it gets, the faster it generates heat. In an atom bomb, the more neutrons it's producing, the faster it generates neutrons. And so the underlying physics similarity, GPT-4 had seen. Now, it probably didn't see it when I asked the question. It had probably seen it during training. So we see a lot of analogies, and we actually store things in the weights. And it's much easier to store things in weights if they're kind of analogous structures, because you can share the weights. And these large language models are just the same. And so in order to store huge amounts of information, they have to see analogies between different facts that they're learning. And they will have seen many analogies that no person's ever seen. And many of those analogies are analogies at a deep level, like between a compost heap and an atom bomb.